Hello, and welcome to my lecture, which is part of the Growth Astronomy School on Observational Techniques and Transient Studies. My name is Christopher Fremling, I work at Caltech, and we are a part of the Global Growth Collaboration. The GROWTH stands for the Global Relay of Observatories Watching Transients Happen. And we have two main goals with this collaboration. As you can see, we have telescopes or locations all around the globe, and the purpose of that is to always be ready to observe when something interesting happens in space. So obviously our focus is transient events such as supernovae, gamma ray bursts, or even gravitational wave events. So that brings us to the second focus, which is to have as much, for every transient, to have as much wavelength coverage as possible. So all the way from radio observations to X-ray and gamma rays, and even to gravitational waves. All right, so today you will be listening to a series of lectures, and the focus of my lecture is image subtraction. So first of all, I will try to convince you or explain why we need to do image subtraction. And here I will be mentioning two of the main applications, I would say. And the first being transient source detection. So to illustrate what this means, I have a series of images here taken by the Stu Parker, who is actually an amateur astronomer who lives in New Zealand, I think. So he runs a small collaboration called the Backyard Observatories Supernova Search, or BOSS. So what they are doing, they are taking images as often as they can, maybe even every night, of some of the most nearby galaxies, and then here we're looking at one of these images, and this would be the image from the next night or the next few nights. And if you have a keen eye, you can actually see that there is a new real point source here, which turned out to be a supernova. Let me go back and forth a little bit here. Maybe you can see it. It's not that easy actually. So I have marked it with an arrow here. So there is a supernova there that appears pretty close to the galactic nucleus of this galaxy. All right. So I mean, this what I just did, flipping between two images like this, is basically what Stu and many of these amateur astronomers do to search for supernova. And it was also the way we scientists, starting with Fritz Zwicky in the 1930s, it's also what they did. They had the photographic plates from one night, compared them to plates from the next, and tried to find any new point sources. And it was actually Fritz Zwicky who coined the term supernova in 1935. So for this task, image subtraction can be of tremendous help. I want to show one more example to really try to illustrate the power of this. And here we are looking at a modern image from the Zwicky Transient Facility, named to honor Zwicky. This is the collaboration that I am part of and working with, trying to search for all kinds of supernovae. We use the Palomar 48-inch telescope. It's not a particularly big telescope, but it has a very wide field of view. So what you're looking at here is one quadrant, is what we call it. So one part of our CCD. But in fact, when we take one exposure with this telescope, we don't just get one image like this, we actually get 64 of them. So there is a lot of data coming in, and in a night we get at least 1,000 images like this. So here I've outlined a small region in this image with this in one quadrant with the green box, and I'm going to show a subtraction on that tiny sub portion of our exposure. So this is zooming in on the green box, and then we perform an image subtraction and we get this. So here it should be much easier to see that there is something that does not go away when we do the image subtraction. It is outlined with the circle here. That was also a supernova. Now, of course, a human could never, go through 1,000 images like this with 64 quadrants and try to flip one image to the next and identify supernova. So that is the purpose of image subtraction on an industrial scale. Combined with machine learning techniques, you can filter out any residuals and only pick out the real transient events, which are in a night of operation of the Zwicky Transient Facility, several hundred thousands. So image subtraction allows you to do transient source detection on industrial scale when combined with advanced computing techniques such as machine learning. All right, but that's not the only application. Second one I will mention here is if you want to study a transient event, it's very important to be able to isolate the light from only your event that you're interested in and remove everything else. So to illustrate what I mean here, I have an image of M82, a very nearby galaxy that hosted a supernova in 2014, for example. So here you're looking at, I just changing the image scaling so you can see a bit more detail. So here is an image from one night, and then a few nights later it looked like this. So very clearly there's a supernova or some transient happening there, which we later identified to be a supernova of type 1a or a thermonuclear event. Supernova 2014J is the name it got. But the point here is, if I go back to the original scaling here, you can see that on that position there is a huge amount of host galaxy light. So if you want to measure the total light from your supernova, you couldn't do it like this, because you don't know the amount of light exactly under the position of the supernova. To remove that, you need to do a host subtraction or image subtraction with exactly the same technique I showed you previously. So here I just want to show the end result of a procedure like that. So I'm showing the light curves or in different filters. So the intensity of light as a function of time at different wavelength ranges, which is the information you need to study the behavior of a transient in order to constrain the physical parameters, such as the total luminosity or how much mass is ejected, etc. So why I'm showing this figure here is because it's from a paper I wrote 5 years ago. And in this paper I describe a full pipeline that will do image subtraction and point spread function photometry. So if you're interested in knowing the details of every step, or all the steps that are needed, take a look at that paper, which you can see on the bottom there, Fremling 2016. All right. So this concludes the first part of the lecture, kind of arguing for why you need to be able to do image subtraction, and I think it should be pretty clear. So now in the second part of this lecture, I will go through the basic steps that you need to be able to do to achieve image subtraction in practice. So all these steps you will be going through in the Jupyter Notebook exercise that follows this lecture. So this is meant as a guide and to introduce you to the concepts. So first of all, you need a science image, obviously, and Perhaps more importantly, you need a reference image taken of the same sky location. And ideally, you would like your reference image to be taken with the same instrument and telescope and photometric filter that you have taken your science image in, because that theoretically that allows you to do more or less a perfect image subtraction. However, in practice, that is rarely possible, especially if you have a telescope with not such a wide field of view, so it becomes unfeasible to image the entire night sky to create a reference catalog. That's the case for most telescopes. But this doesn't mean that image subtraction will be impossible. You could go back a few years later after your transient happened and take a reference image when it has disappeared. But of course, that's not very efficient if you want to do science on a rapid time scale. Instead, I would suggest that you try to use some of the very nice all-sky surveys that have now been done, such as Pan-STARRS 1 or the Sloan Digital Sky Survey. So they have already imaged the entire sky, especially the northern sky in the case of SDSS, in a range of photometric filters. And these images can be used as your reference images in many cases, as long as the photometric filter you are using is close enough to the filters used by PS1 and SDSS. So this is what I have been doing a lot for the Zwicky Transient facility. We have a small, actually it's bigger than the survey telescope. It's a 60-inch telescope, but it's small in the sense that there are 10-meter telescopes out there. But it's a good telescope to do follow-up imaging of supernovae. So for that, that telescope has not a very big field of view, so we cannot always obtain reference images. Instead, I'm using the PS1 and SDSS, depending on which one is available. All right. So how to do image subtraction in practice? Now we have our science image or reference image. The next step is to align your images in pixel space, because that's where they live in your computer. So basically, if you take an image of the same location on the sky with your telescope on one night, and then you take another, or you attempt to take another of the same position the next night, it is very likely that your stars will not end up on exactly the same pixel coordinates in your image because of many reasons. The main one being that the stars move around, we are in everything is going around in circles or ellipses in space. And then depending on the time when you observe, your rotation of your telescope may be different and things like this. And it more or less becomes unfeasible to try to get your stars in exactly the same pixel every time. It's just not a good idea to even try to do that. Instead, what you have to do is something called astrometry, which is based on the simple fact that the stars are always at the same right ascension and declination. Okay, the second step you have to do is point spread function matching, which has to do with matching the conditions at the time you're observing. So let's say I take an image tonight and then another image tomorrow. There is no guarantee that the weather conditions, temperature, clouds, etc., will be the same, and all that will affect very strongly how the light is spread out as it passes through the atmosphere from space and into your detector. So that you will have to take into account. All right. Finally, here I have something called 0-point matching, and that In simple terms, it just means that you want your static sources, the stars in your science image and your reference image, to have the same intensity or the same count, so that when you subtract your two images, the stars will subtract out to 0. So practice, you just have to scale one image until the stars match in strength to the other image. But here again, it can be very useful to have these catalogs such as SDSS and PanStars1, especially if you want to put your measurements on some magnitude scale, such as the AB magnitude scale. Then you need to know some known magnitudes of some stars in the image, which you can collect from these catalogs. All right, having done these three main steps, basically the only thing that remains is to do a subtraction of your reference from the science frame. All right, yeah, and as I said, you will be going through these steps when you go through the Jupyter notebook. And now I will give some more details on each of these three things. All right, first of all, to perform image alignment, as I said, you need to solve your image, or you need to create an astrometric solution for your image, which just means you need to tie the pixel coordinates of the stars to known right ascension and declinations. Fortunately, the night sky has been imaged by so many telescopes and projects now, so that we have maps or catalogs of how the night sky will look for any given position. And in particular, what's used here is the geometry between stars. You can group them into triangles or squares or some geometrical shape, and then you can run a matching algorithm to match up what you have in your image to what should be there based on the array and dex. Doing that from scratch would be, that would be an incredibly large task. But fortunately, there are packages made that will make this very easy for you. One of them is called astrometry.net, and another is called Scamp. Right, so when you know the positions of the stars in your reference image and your science image in array and deck, you can very simply or very easily figure out which stars are present in both the science and the reference image. Knowing that, you get a list of common stars, and then you can create a geometric mapping that will take the geometry of one image and translate it into the same as in the other image. The simplest case perhaps being you look at two images and maybe you will see that one is just shifted a little bit in horizontal and vertical axis, and then you just need to apply a simple constant shift. And then, of course, the final step when you have your geometric mapping is to actually transform one image, translation, rotation, scaling, or whatever. That step is also quite, it can be mathematically challenging, but there are packages that will do this for you in Python, MATLAB, or IDL. Most basic coding packages will have this capability. Okay, so just to illustrate the basic, the simplest case here is I have two images from the Palomar 60-inch telescope taken on consecutive nights, and you can see, I have aligned them in pixel coordinates, and it's very clear that the stars and this galaxy, they don't turn up at the same position. Actually, the stars in the image on the right is a bit above and to the left in this case, which I outlined with the orange circles. So based on the RA index and the astrometric solution, I know that those are the same stars. And then to move those circles to the green circles is not such a difficult thing, it's just a translation. However, I should point out that the difference can be much greater between images, in particular if you use reference images from a different telescope or project compared to your own. Then it's very likely that the pixel scale will be different, the rotation can be vastly different. Your image could be flipped 180 degrees. And you can have quite strong distortions depending on the pixel coordinate. That will depend on the optical design of your telescope. But as long as you know the RA index of some common stars, all this can be solved by using pretty basic matrix operations. And if you remember some of your basic maths, you will know that image translations and scalings and rotations can be described by these 3x3 matrices. And then you can potentially also combine any number of translations, scalings, rotations, etc. There is also a matrix that would describe polynomial transformation. Okay, so we have our geometric mapping. The final step is then to transform one image so that it ends up in pixel coordinates right on top of the other. For example, translation. However, I should point out that this step in particular, you cannot just do it roughly. If one image is shifted by 8.6 pixels, it's not fine to shift by 9 full pixels. That's not going to be good enough. So these steps, it really needs sub-pixel accuracy. So as a thought experiment to the listeners here, I want you to think about if you have an image in your computer with a fixed pixel grid, fixed size, how can you shift this image in some direction by half a pixel? Think about that, and we can discuss the answer on the live session that will follow this. But I should say that all these 3 steps, many astronomers have thought about them and they have solved them, and there is not really a need for you to, invent the wheel again. So I'm listing some tools here that you can use to achieve these things. Point 1, you can do with Extractor. Point 2 with Scamp or astrometry.net, and point 3 with, for example, Swarp or MATLAB or Python. There will be native Python tools that will do image transformations. Okay. Second main step in image subtraction, as I listed them, is point spread function matching. So to illustrate the purpose of this or what it means, I have 2 images here that I believe are illustrative. So on the left you can clearly see that the image is much more detailed, sharper, and on the right it looks smoothed out. And this is because of different observing conditions at the time when the images were taken. So if you would just do one image minus the other here, you would get lots of residuals because the stars are basically not the same, not even the same size on your image. So this you will have to account for. And again, to do this, I broke it down to 3 steps. First, being very similar to the image alignment, you need to detect stars in your images. But in this case, you have to be a bit more careful. You don't just need any source or any star. You need to make sure that they are really stars or point sources, because that is what the point spread function describes. What happens to a true point source in space as the light travels through the atmosphere and into your telescope optics, and finally to your detector. So you may want to look at how your image looks. First of all, do you have sources in it that clearly are less elongated or more circular? Then those are probably your stars. There are, as I said, there are packages that are very good at this. For example, there is one called PSF extractor, which builds on the source extractor. Right, so when you have your list of true point sources, you need to take all of them or as many of them as possible and construct a model of the PSF in your image. Simplest case is you just stack them all on top of each other and do a median. That will work fairly well, but it would not be able to account for the case, which is possible, that the PSF is actually changing as a function of position in your image, which will be depend on the optics again in your telescope. Right, but to deal with that, you would need to, or it would be the simplest probably to fit some parametric model to your good point sources, and then figure out how does this equation change as a function of position in the image. But you could do it fully empirically as well. Right. So when you have PSF models of both the reference image and the science image, all that's left to do is to convolve one image or both in order to match these PSFs. So I will try to illustrate the simplest method to do this, like this here. So imagine we have the PSF of the reference image in the top row here, and of the science image in the bottom row. So the first images starting from the left would be how things look from space, which would be the same in your reference and science frame. But then the light travels through the atmosphere, and the reference PSF becomes a bit worse. You can see on the second top row from the left, and much worse for the science frame. So what you can do then is, because fortunately convolutions are commutative, you can just take the PSF of the reference, apply that to your science image, and take the PSF of the science image, apply that to the reference image, and then you will achieve exactly the same PSF, which is shown to the right, in the rightmost panels here. So because the order doesn't matter, you will end up with the same PSF. Right, so that's usually called a common point spread function method, for example, which is the method I used in the paper I mentioned earlier in the Fremling 2016. And it's not exactly the same, but the method we are using in the industrial scale Zwicky transient facility pipeline is based on this method. So I mean, it's true that you are degrading both the science and reference frame when you do this, but it's not. That doesn't mean that the method is inferior. It has been working very well for us, and the implementation we use in ZTF is called SOGI. And if you want to know exactly how that works, it's described in this paper by Sakei et al. In 2016, which I have here in the center of the slide. All right, but as I said, this is not. That's not the only way to match PSFs. You could instead, if you prefer to not alter your science image, you can figure out how would you have to degrade just the reference image for it to match the science image in terms of PSF. Now, unfortunately, figuring that out will require that you take the PSFs to Fourier space, first of all, and then you perform a division. And this, if you're not very careful, this has a tendency to introduce ringing artifacts when you then treat the reference image with this kernel. However, you may get a better result if you use parametric models which will have absolutely no noise. And this has been used in a very successful method which was pioneered by Allard and Lupton in 1998. And it's an interesting paper. You can try to read that if you want to understand PSF matching in the case where you only degrade one image. So basically they they turn the thing into an optimization problem. You assume a parametric model for your PSF, and then this code will just look at your science and reference image and figure out the optimal way to degrade, usually the reference image. And that we used that method in the precursor project to the ZTF. We used it in IPTF. However, it's still, because you have to, you need to parameterize the PSF. You will have many parameters that are changing potentially from one image to the next. It means that it can be tricky to make it perform the same every time. And you still can get some Fourier artifacts even with the parametric PSF. Okay, so we have reached the final step required to do image subtraction, which I am calling here 0-point matching. And you know, in the simplest case, you just measure the flux in all the stars in one image, and then you scale the other image until you get the same measurement for the same stars in that image. Then you're done. However, that would not allow you to measure what are the magnitudes on some fixed scale, such as the AB magnitude scale, because you haven't tied your image to any reference. So instead, I would suggest that you use a catalog such as PS1 or SDSS. Then you measure the magnitudes in your image and you figure out the 0 point to get the same magnitudes as in PS1. And you do that for both of your images, and then you apply a scaling to one of them until you have the same 0 point. Okay, and that will allow you to subtract the reference from the science frame, and then you are in principle done. So those are the three main steps you will have to do, and I want to end with just an example which I believe is the exactly what you will be doing in the Jupiter notebook exercise. So here's an image from the P60 telescope, the Palomar 16-inch. There is a supernova in this galaxy, and your task is to find it. It's pretty difficult just by adjusting the image scaling, but on the left I'm showing the raw image, and on the right I have performed the subtraction using exactly the notebook that you will be using. And then it becomes quite simple to find this supernova there outlined in the red circle. So, by the way, that's PTF12OS, one of the supernova I studied in the paper I mentioned earlier. Okay, so that concludes my lecture. I hope to see you all in the live session that will follow this, and also in the Jupiter notebook exercise. So all this lecture and the notebook will be made available on the webpage. You can see the link there. Thank you.